Welcome. This is a review of lesson 5, and we're going to break this into two videos. So we're going to have first a quick review video on exothermic reactions, and then we're going to have a quick video on endothermic reactions. The key thing to make sure that you understand going into this is that the products of an exothermic reaction are going to be lower in potential energy, compositional potential energy, than the potential energy of the reactants. So the reaction that I'm modeling this with, and we actually did this with two different reactions. This was the first one that I talked about, and that's where we take solid sodium hydroxide, we put it in water, we allow it to dissolve. This is an ionization reaction. All right, and so to build our universe, we're going to have a container here, which could be a glass, and in it will be liquid water. This represents our surroundings, and it's going to be at a particular temperature. We'll just call it room temperature. All right, and then inside this, we're adding the reaction, and we're going to conceptualize it as being a compartment. This is called the system. So the chemical reaction is the system. And I'm going to put the reaction down here so I have a little bit more room to work with. So once we add the NaOH to the water, if you were holding this glass of water in your hand, you would feel it start to heat up. And the reason for that is because we have an exchange of energy going on. The sodium hydroxide, the solid, is an ionic bond. And the ions in the products are bonded to water. So what we have going on is we have bonds that are breaking and bonds that are forming. The bonds that are breaking are ionic, and the bonds that are forming are between water and the ion. In this exchange, the reaction is going to have a change in potential energy, and what that's going to look like is the potential energy of the system is going to drop, and the potential energy of the surroundings is going to increase. So you can look at this another way. We can look at it from the point of view of also kinetic energy. So there's going to be a gain in kinetic energy out here. And where that's coming from is the difference in energy between where we start with the reactants and where we finish with the products. So if we graph this and we put potential energy on the vertical axis, the reactants are going to start in a certain location. I'll just arbitrarily pick this point right here, and we'll write NaOH. And we'll call this, if you want, PE1. All right, and then where this finishes, the products are going to be on a line which is lower because they're lower in potential energy when this is done. All right, so we're going to have Na plus OH minus here. And you can see, you need to spend some time with this and think about it, that if I draw a line over here, this is PE2. And down here, this is 0. So look, PE2 is less than PE1. So there's an energy difference here between these two, this gap. And what this gap represents is going to be the kinetic energy of the surroundings. This is why, and I'll put it in words, this is why the temperature rises. You feel the glass get hot. You feel the glass get hot. And the reason that it is because during this reaction there's a shift in potential energy. And the products of the reaction are lower. Okay, let me just spell this out. Products are lower in PE. End of story. Okay, so I'm going to go ahead and conclude this review, and it will be posted shortly on your page.